In this episode of the Quantum on the Back of an Envelope series, we'll ask whether a quantum mechanical wave function really has to vanish at infinity, an assumption often made in introductory textbooks and courses on the subject. For simplicity, let's restrict our discussion to the case of a quantum particle on an infinite line, represented by the x-axis. Suppose the particle is described by a wave function psi of x. The probability density of finding the particle at a given position is given by the squared modulus of psi. This probability density must satisfy the normalization condition, which requires that the integral of the squared modulus of psi over the entire line equals 1. It is often argued that this normalization requirement implies the probability density, and therefore the wave function itself, must vanish at infinity, with psi of x approaching 0 as x tends to plus or minus infinity. Strictly speaking, however, this logic is flawed. To see why, consider this example of a perfectly normalizable wave function that does not, in fact, vanish at infinity. Here, c is a normalization constant. The corresponding probability density is given by this expression. The graph of this probability density shows an infinite sequence of sharp peaks occurring whenever x is a multiple of pi. The larger the value of x, the sharper and taller the corresponding peak. This density function is continuous, differentiable, and most importantly, normalizable. We'll return to the question of normalizability in a moment. In this example, the wave function psi not only fails to vanish as x tends to plus or minus infinity, it actually becomes unbounded at infinity. To confirm that the wave function is normalizable, it is enough to show that the area under the tails of the probability distribution is finite. Let's consider the nth peak and write x as pi times n plus a small displacement epsilon, where n is taken to be very large. Expressed in terms of epsilon, the peak has an approximately Gaussian shape. The area under the peak can be evaluated by performing the corresponding Gaussian integral. A straightforward calculation shows that the area decays as 1 over the square of n. The total area under the tails of the probability distribution is then obtained by summing all the peak areas, giving the following sum. This sum is convergent, which means the total area under the distribution tails is finite. This example demonstrates that the normalizability of psi does not necessarily imply that it vanishes at infinity. However, it can be proven that if both psi and its derivative are normalizable, then psi is indeed guaranteed to vanish at infinity. We hope you enjoyed this episode of Quantum on the Back of an Envelope. To learn more about what we do, please visit us at our website.